Okay, let's really get into this. Picture this. You're on a train, yeah, just cruising along nice and smooth.
Right.
And inside the train car, everything feels totally normal. You toss a ball straight up in the air, and, just like you'd expect, it comes straight back down into your hand. Feels simple, right? Just gravity doing its thing.
You see, straightforward enough.
But now, think about someone standing still on the platform, watching your train zoom past.
Okay, different perspective.
From their viewpoint, when you toss that ball up, it doesn't just go straight up and down, because the train's moving.
The ball's moving forward, too.
Exactly. So they see the ball go up and forward, tracing this kind of arc through the air.
A curved path, yeah.
So here's the big question, the one that kind of messes with your head. In terms of what's really happening, who's right? Is it you, on the train, seeing the ball go straight up and down? Or is it the person on the platform seeing it curve forward?
And that's the fascinating bit, isn't it? And it's really the jumping off point for this whole deep dive based on the stuff you shared. According to Albert Einstein's theory of relativity, well, the answer is they're both right.
Both. How can they both be right?
Because their different viewpoints, their different frames of reference, fundamentally change what they actually observe about the ball's motion. Yet both observations are completely valid within their own context.
It depends on where you're observing from.
Wow. Okay. And that simple train example, which sounds like a contradiction, that's our way into one of the most, well, profound and definitely mind-bending scientific ideas ever thought up.
Absolutely.
So this deep dive is all about Einstein's theory of relativity. And, the material we're looking at makes it really clear up front. It's not just one single idea. It's actually two massive theories.
That's right. First, there was special relativity back in 1905. That deals with motion, but specifically motion at constant speeds and how that affects things like space and time.
Okay, constant speed, like our smooth train. Exactly. Then, about 10 years later, 1915, he came out with general relativity. And that expanded things to include acceleration. And, crucially, it completely changed how we understand gravity.
So 2 parts, special and general. Got it.
And our goal here, for this deep dive, sticking closely to the sources you've got, is to take these really revolutionary, often counterintuitive ideas about how time, space, mass, energy, gravity, how they all actually work and, break them down.
Make them make sense.
Yeah, try to illuminate the key insights using language that's accessible and really lean on the simple but powerful examples and analogies that are right there in the source material. No scary equations, no confusing jargon, just trying to make the seemingly impossible understandable.
Because it's easy to forget, before Einstein, the universe felt more fixed, didn't it? More predictable, almost, looking back, kind of naive.
Yeah, people really thought of time as this universal clock, just ticking away exactly the same rate for everyone, everywhere, no matter what.
Didn't matter if you were sitting still or flying across the globe, time was time.
Right, and space. Space was just there. An empty stage, a fixed backdrop for everything to happen against.
And gravity was just, gravity. This weird invisible force just pulling stuff together like a cosmic string or something.
Like a giant magnet, maybe. But then Einstein comes along, and with this incredible intellectual bravery, he basically says, hang on a minute. What if time isn't the same for everyone? What if space isn't just a static backdrop? What if gravity isn't really a force in that way? What if reality is actually much more flexible, more dynamic, more interconnected than we ever guessed?
It's such a huge conceptual leap.
It really was. His work didn't just, add a few pages to the physics books. It was like he tore up the old book and started writing a completely new one. He didn't just adjust our understanding. He changed the fundamental rules of how we thought the universe worked.
So it shifted from this idea of everything being kind of fixed and separate
to a universe where time and space are woven together, where matter and energy are just different forms of the same thing, and where gravity isn't some mysterious pull acting through space, but it's actually a property of space itself. The impact of that shift, it's hard to even put into words how massive it was.
Okay, let's tackle the first part then, the foundation stone. Special relativity came out in 1905, often called Einstein's miracle year, right?
That's the one. An incredible year for physics.
And this is where our everyday, common sense understanding of reality starts to get, seriously challenged. Special relativity looks at the relationship between space and time, specifically in what physicists call an inertial frame of reference.
Which basically just means when you're moving smoothly, at a constant speed in a straight line. like our train example again, assuming it's not accelerating or turning.
Right, and the really big idea here is how time and space behave differently for observers who are moving at different constant speeds relative to each other.
And this flies directly in the face of that gut feeling we all have, that deeply ingrained belief that time just ticks along at the same rate for everybody.
Yeah, it feels absolute. A minute for me is a minute for you, no matter what.
It feels that way, absolutely. But special relativity introduces this core, definitely counterintuitive, but experimentally proven idea called time dilation.
Time dilation. Okay, even the name sounds like sci-fi, like, warp speed problems on a starship.
It does have that feel. But according to the source material we're working from, and just decades of scientific confirmation, it's very real. It means time itself. The actual flow of time can literally slow down or speed up depending on how fast you're moving compared to someone else.
Wait, not just your watch slowing down, like time itself slows down.
That's the crux of it. The actual rate at which time passes for you is different from the rate it passes for someone moving differently. Your speed literally affects how time flows in your frame of reference.
That's why.
It is. And the classic thought experiment used to really illustrate this, the one that's highlighted in the source material's explanation, is the famous twin paradox.
Ah, the twin paradox. Heard of it, but maybe you can walk us through it again.
Sure. So imagine you have two identical twins. Let's call one, say, the Earth twin. She stays right here on Earth.
Okay, homebody twin.
Right. The other twin, the space twin, she hops on this incredibly fast spaceship. A hypothetical ship, obviously, capable of traveling at speeds really, really close to the speed of light.
Near light speed. Got it.
Now, from the perspective of the space twin on her ship, the journey takes, let's imagine, exactly 1 year. She lives through 365 days, has one birthday on board, experiences 1 year passing.
Seems simple enough for her. 1 year trip.
But, and here's where special relativity really shows its strangeness, the paradox part from our normal point of view. When that space twin finally returns to Earth after what felt like just 1 year to her, she finds her Earthbound sister has aged significantly more. Maybe 10 years have passed on Earth, maybe 20, maybe even more, depending on just how close to light speed the ship was traveling.
Whoa. So 1 year for the space traveler, but 10 years for the one who stayed home. How is that possible?
That's the core of the paradox, right?
Right.
And it's not just a clock issue. It's a real difference in the amount of time experienced by each twin. It happens because of their different relative motion. It really just blows up our everyday idea that time is this single universal river flowing the same for everyone.
It really does. So how does special relativity actually explain why this happens? Why does the space twin age less?
It comes down to the fact that the space twin's incredibly high speed directly affected the flow of time for her. In her frame of reference, moving so fast relative to Earth, time literally ran slower compared to the Earth twin's frame of reference, which was, relatively stationary. It's just a fundamental rule of how motion affects time in our universe.
So my personal now isn't necessarily your personal now if we're moving differently.
In a very real sense, yes. And the rate your timeline progresses isn't universally shared.
Okay. Mine's slightly blown already.
And this weird stretching of time dilation, and also a related effect where space actually contracts in the direction of motion. These are necessary consequences of what might be the single most fundamental rule underpinning special relativity, and maybe one of the deepest truths about our universe.
Which is?
There's a universal speed limit. Nothing with mass can ever reach, let alone exceed the speed of light in the vacuum.
Ah, see,
Wow.
the cosmic speed limit. Around 186,000 miles per second.
Or 300,000 kilometers per second, yeah. And it's not just that light is super fast. It's that this speed is a fundamental constant of nature. It's the absolute maximum speed limit for any information, any cause and effect to travel through the universe. Our source material really emphasizes this. The constant speed of light is the bedrock. Everything else in special relativity builds from that.
Okay, so light speed is constant. How does that lead to time slowing down?
Well, think about it. If the speed of light must be measured as the exact same value, c, by every observer, no matter how fast they themselves are moving.
Right, that sounds weird too. If I'm chasing a light beam, shouldn't it seem slower to me?
Intuitively, yes, but experiments show it doesn't. Light speed is always c, regardless of your own motion. So, if the speed of light won't change, something else has to give. Our comfortable, intuitive ideas of rigid space and absolute time, They have to break.
Ah, okay. So to keep light speed constant for everyone.
Space and time themselves must become flexible. As an object speeds up, getting closer and closer to see, from the perspective of someone watching, space must actually shrink or contract for that object in its direction of motion. And, crucially for the twin paradox, time must slow down for that fast-moving object.
Time slows down so that the speed of light remains constant for them.
Exactly. These distortions of space and time are the universe's way of enforcing that ultimate speed limit. Things don't just keep getting faster indefinitely. The very fabric of reality space-time stretches and bends to make sure nothing with mass ever hits psi.
So time isn't like a fixed river flowing at the same speed everywhere. It's more like the flow changes depending on how fast you're moving through it.
That's a pretty good analogy, actually. The faster you move through space, the slower you move through time, relative to someone who's moving slower through space. It was a completely revolutionary concept that forced physicists to ditch centuries of ingrained thinking.
A total paradigm shift.
Absolutely. And special relativity didn't just stop there with time and space. It also uncovered this incredibly deep, unexpected link between two things we normally think of as totally separate: mass and energy.
Okay, now we're getting to the famous one.
This brings us to arguably the most famous equation in the history of science. Everyone knows it, even if they don't know what it means. EMC-FAFOs.
EMC-FO. Energy equals mass times the speed of light squared. It's iconic, definitely. But what does it really tell us, in simple terms, based on our sources? What's the core idea?
At its heart, it's saying that mass and energy are basically interchangeable. They're just two different forms of the same fundamental stuff. You could call it mass energy.
So mass can turn into energy, and energy can turn into mass.
Exactly. They're deeply connected, like two sides of the same coin. Not separate things at all, fundamentally.
And that core part of the equation, the speed of light squared, that must be a huge number.
It's astronomical. The speed of light is already enormous, around 300 million meters per second. Square that, and you get 90 quadrillion. It's a gigantic multiplier.
So if you take even a tiny, tiny amount of mass, the m, and multiply it by this enormous section,
the resulting amount of energy, the E, is absolutely immense. The equation reveals just how much incredible energy is locked away inside matter itself just by virtue of it having mass.
Wow. And the source material gives some pretty potent real-world examples of this, right?
It does, both destructive and constructive examples showing the sheer power of this principle.
On the destructive side, this is the basis for nuclear weapons, isn't it?
Fundamentally, yes. In an atomic bomb, during a nuclear reaction, fission or fusion, a very small fraction of the mass of the atoms involved, like uranium or hydrogen isotopes, gets converted directly into pure energy. And because CZ is so huge, even that tiny bit of mass releases a catastrophic amount of energy. It's matter turning into raw power.
A terrifying demonstration of the equation.
Indeed. But on the constructive, and arguably much more important side for life, EZO also explains how our sun works. How all stars shine, really.
The sun's power comes from this. How?
The sun is constantly undergoing nuclear fusion in its core. Essentially, it's smashing hydrogen atoms together under immense pressure and heat to form helium atoms.
Okay.
But here's the key. The total mass of the helium atoms produced is slightly less than the total mass of the hydrogen atoms that went into the reaction. A tiny bit of mass disappears in the process.
It just vanishes.
Not vanishes, it gets converted directly into energy, according to EMCY.
Wow.
And that released energy is the heat and light that radiates out from the sun.
So the sunlight hitting us right now, that's literally converted mass from the sun.
Precisely. Every photon warming your skin, every bit of light reaching Earth represents a tiny amount of the sun's mass that has been transformed into energy. The sun is constantly losing mass as it shines, continuously proving Einstein's equation on a cosmic scale. It's not magic, it's just fundamental physics.
That's incredible. So just to recap special relativity from 1905, it hit us with these huge ideas. Time isn't fixed, it depends on your speed. Space isn't fixed, it's linked with time. And mass and energy are basically the same thing, linked by the speed of light.
It completely rewrote the rules. Before Einstein, you had Newton's universe. Absolute time ticking everywhere, absolute space as a stage. Special relativity smashed that picture. It showed time as relative, interwoven with space into the single entity we call space-time.
It must have been such a shock to the scientific community, and even just to the way people thought about the world. This idea that time itself could be different for different people.
Oh, absolutely. It wasn't just counterintuitive. It challenged fundamental assumptions that had stood for over 200 years since Newton. It wasn't just a new theory. It felt like a new reality.
But, as the source material tells us, Einstein realized special relativity was incomplete. It worked for constant speed, but what about speeding up, slowing down, changing direction?
Exactly. What about acceleration? And maybe the biggest question left hanging, what about gravity? Special relativity didn't really incorporate gravity. That led him on another decade-long intellectual journey.
Okay, so let's move forward then. 10 years after special relativity, we get to 1915. And Einstein publishes his theory of general relativity. And this one,
This is all about gravity, right?
this is his masterpiece on gravity. And again, it completely overturns the previous understanding.
Gravity, I mean, it feels so familiar, doesn't it? We live with it constantly. Drop something, it falls. Jump up, you come down. It's the force we experience most directly. And the old idea, the Newtonian picture from the 1600s, was that gravity is just that, a force, an invisible pull between objects that have mass.
Like Earth pulling on the apple, the sun pulling on the Earth. More mass means a stronger pull. Seemed to work pretty well.
It worked incredibly well for centuries. It explained planetary orbits, tides, falling objects. But Einstein looked deeper. He wasn't satisfied with just saying it's a force acting at a distance. He wanted to know how it worked. And his answer in general relativity was radically different.
So what did he propose instead of a force?
He proposed that gravity is not a force pulling things across space. Instead, gravity is the effect of massive objects like planets, stars, even you and me, actually bending and warping the very fabric of space and time around them.
Whoa, so mass doesn't create a force field, it bends reality itself.
In a manner of speaking, yes. Think back to that idea of space-time from special relativity, this interwoven fabric. General relativity says that mass and energy, because remember, UC knows, tells space-time how to curve. And that curvature of space-time, in turn, tells mass how to move.
Okay, that's pretty abstract. How can we visualize that? The source had a good analogy, didn't it?
It did, the classic one, the rubber sheet analogy. Imagine you have a big sheet of rubber stretched out flat and tight, like a trampoline.
Okay, got the trampoline in my head.
Now place something heavy in the middle, like a bowling ball. What does it do to the sheet?
It sinks down, right? Creates a big dip, a curve in the rubber around the ball.
Exactly. The heavier the ball, the deeper the dip, the more the sheet curves. Now imagine you take something smaller, like a little marble, and you try to roll it across the sheet near the bowling ball.
It wouldn't go straight anymore.
Right. It wouldn't travel in a perfectly straight line as it would on a flat surface. Its path would curve. It would be deflected by the dip the bowling ball made. If you roll it just right, it might even start circling around the bowling ball, kind of like an orbit.
Ah, okay. And the crucial point here is that the marble isn't being pulled by the bowling ball with some invisible string or force, right?
Precisely. It's simply following the easiest, most natural path available to it on the curved surface of the rubber sheet. Its motion is dictated by the shape, the geometry of the bent sheet itself.
So translating that back to the universe.
According to general relativity, this is exactly how gravity works. Massive objects like the Earth are the bowling ball, sitting on the cosmic rubber sheet of space-time, creating a local dip or curve. The Sun, being much, much more massive,
Creates a much bigger, deeper dip in space-time.
a much more significant curvature. So when the Earth orbits the Sun, Einstein's theory says it's not because the Sun is exerting some mysterious long-distance pulling force on us. Instead, the Earth is simply following the curved path in space-time that the Sun's immense mass has created. We're essentially rolling along the contours of the dip caused by the Sun's presence in the fabric of space-time. Motion determined by geometry, not by a force.
So gravity isn't a force in space, it is the shape of space-time.
That's the essence of it. Objects just follow the straightest possible lines called geodesics through this curved space-time. What looks to us like a force pulling things is actually just objects following the natural curves created by mass and energy. It's a mind-bendingly different way to think about it.
Okay, that's a beautiful idea. But science needs proof, right? Did general relativity make predictions that could actually be tested? Predictions different from Newton's theory?
Absolutely. That's the hallmark of a good scientific theory. And general relativity made several testable predictions. One of the most dramatic, highlighted in our source material, was about light.
Light. But light doesn't have mass. Newton's gravity shouldn't affect it, should it?
According to Newton, no. Gravity was about mass attracting mass. But Einstein's theory said gravity is the curvature of space-time itself, caused by mass and energy. And since light travels through space-time,
Its path should also be bent if it passes through a region where space-time is curved by a massive object.
exactly, even massless light should follow the curves. This was a clear prediction that differed significantly from Newtonian physics.
So how could you test that? You'd need a really massive object to see the effect.
The most massive object nearby is the sun. The prediction was that starlight passing very close to the sun should have its path bent by the sun's gravity, by the curvature of spacetime near the sun.
But you can't see stars near the sun normally, right? It's too bright.
Correct, except during one special event, a total solar eclipse.
Oh, when the moon blocks the sun's light completely.
Precisely. And that opportunity came in 1919. The source mentions expeditions, led by the British astronomer Sir Arthur Eddington, traveled to locations where a total solar eclipse would be visible. Their goal was to photograph the stars that appeared very close to the edge of the sun during the brief minutes of totality.
Okay, so they photographed the stars during the eclipse. Then what?
Then they compared those photographs to pictures of the same group of stars taken months earlier when the sun was in a completely different part of the sky, so its gravity wouldn't be affecting the starlight's path to Earth.
And what did they find? Did the stars' positions change?
They did. The results were stunning. The stars whose light grazed the sun during the eclipse appeared slightly shifted outward, away from their normal positions. Their light had been bent as it passed through the curved spacetime near the sun.
And crucially,
the amount of bending, the angle of deflection, matched Einstein's predictions from general relativity almost perfectly. It was significantly different from what Newton's theory would predict, which was either zero bending or only half the amount if you try to force light into the old framework.
wow, direct observational proof.
Monumental proof. It was confirmation that Einstein's radical new picture of gravity as warped space-time was correct. And as the source notes, this confirmation, coming right after World War I, captured the world's imagination.
It made Einstein famous overnight, didn't it?
Instant global celebrity. This obscure German-Swiss physicist who'd been pondering the universe. Suddenly, he was the man who had rewritten the cosmos, and the stars themselves had proven him right during this dramatic celestial event. It was an incredible scientific and human story.
Okay, so we have special relativity. Time and space are flexible, linked to speed. And general relativity. Gravity isn't a force, it's the curvature of space-time caused by mass and energy, and even light follows these curves. These are huge, cosmic ideas. Twin paradoxes, bending starlight. It still feels a bit remote, maybe.
You can feel that way dealing with light speed and stars.
So let's bring it down to Earth, or maybe just above Earth. What does all this mind-bending physics actually mean for you, listening right now, in your everyday life? Is there a practical application?
Oh, absolutely. And one of the most direct and frankly essential examples that our source material points to is something millions of us use every single day. The Global Positioning System, or GPS.
My phone's map, the navigation in my car. That uses relativity,
Seriously. That little dot showing you where you are, the voice telling you to turn left. It wouldn't work accurately for even a few hours without engineers constantly applying corrections based on both special and general relativity.
No way. How does my phone needing directions involve Einstein?
It all boils down to incredibly precise timing. GPS works because your phone or device listens for signals from a network of satellites orbiting the Earth.
Right, there are GPS satellites up there.
And these satellites carry extremely accurate atomic clocks. Your device figures out your position by calculating how long it took for signals from several different satellites to reach it. Tiny differences in arrival times let it triangulate your location.
Okay, makes sense. Needs good clocks.
Extremely good clocks.
Huh.
But here's the catch. According to relativity, those clocks on the satellites don't tick at the exact same rate as identical clocks down here on the ground. They're affected by two different relativistic effects happening at the same time.
Two effects. Okay, what are they?
First, those satellites are moving really fast. They orbit Earth at about 14,000 kilometers per hour, something like that.
Pretty quick.
Very quick relative to us on the ground. So according to special relativity time dilation, due to speed, their clock should actually tick slightly slower than clocks on Earth.
Okay, effect one. Speed makes satellite clocks run slow.
Got it. But then there's the second effect from general relativity. The satellites are orbiting high above Earth, much farther from the center of Earth's gravity than we are. They're in a weaker gravitational field.
Right. Gravity gets weaker the further away you are.
And general relativity predicts that clocks run faster in weaker gravity. The weaker the gravitational pull, the faster time passes.
Whoa, hang on. Special relativity says the satellite clocks run slower because they're fast, but general relativity says they run faster because they're in weaker gravity. They contradict.
They push in opposite directions, yes. So which effect wins? In the case of GPS satellites, the effect from general relativity of the speeding up due to weaker gravity is actually significantly stronger than the slowing down effect from special relativity due to their speed.
Really? How much faster do they run?
Our sources indicate the numbers are roughly like this. The weaker gravity makes the satellite clocks gain about 45 microseconds. That's millionths of a second, every day compared to ground clocks. The high speed makes them lose about 7 microseconds per day.
Okay, so 45 faster minus 7 slower. Net result is they run faster by about 38 microseconds each day.
Exactly, about 38 microseconds per day faster than clocks on the surface of the Earth. Now, 38 millionths of a second sounds incredibly tiny, right? Insignificant.
Yeah, seems like nothing.
But GPS relies on timing signals that travel at the speed of light. And light travels incredibly fast, about 30 centimeters or 1 foot in just 1 nanosecond, billionth of a second.
Okay.
So an error of 38 microseconds per day in the satellite clocks. That timing error translates very quickly into a position error on the ground because you're calculating distance based on that time measurement. Distance is speed of light, x time.
I see. If the clocks are off by even a tiny bit and you multiply by the huge speed of light, the distance calculation goes wrong.
Precisely. If the GPS engineers didn't constantly use Einstein's equations, both special and general relativity, to correct for this 38 microsecond per day difference, the system would fail spectacularly. The calculated position errors would build up really fast.
How fast? How wrong would my phone be?
Within just the first day, the uncorrected errors would lead to your reported position being off by several kilometers, maybe as much as 10 or 11 kilometers, or about 7 miles.
Miles. After just one day. Wow. So the map would be completely useless. It might tell me I'm in the next town over.
Or driving through a building, or in the middle of a lake. It would be wildly inaccurate. Modern navigation, precision agriculture, emergency services, financial networks, timing, so much relies on accurate GPS. And accurate GPS relies directly on engineers accounting for Einstein's relativistic effects on time.
That's incredible. It's maybe the most tangible everyday proof that these seemingly abstract theories about space and time bending aren't just blackboard exercises. They're literally built into the technology that structures modern life.
It really drives home that relativity describes the actual fundamental operating system of our universe with real, measurable, and economically vital consequences.
Okay, so pulling back again, why does this theory, these two theories, really matter to you, the listener, beyond just making your GPS work?
Our source material kind of sums up the bigger picture impact. Well, fundamentally, Einstein's theories gave us a completely new vision of the universe. It's not the rigid clockwork machine Newton envisioned. It's far more complex, more interconnected, more dynamic, and frankly, much stranger and more wonderful.
Time isn't absolute, it's flexible. Space isn't just empty, it stretches and bends. Mass and energy are two sides of the same coin, and gravity isn't a spooky force, it's the shape of space-time itself.
And this radical new understanding didn't just change physics. It paved the way for whole new fields of science and technology. Things we often take for granted now.
Yeah, the source lists several key technologies that stem from or were heavily influenced by this new physics. We already talked about GPS and satellite communication, which need those relativistic corrections.
Right.
Lasers are mentioned too. Now, lasers are complicated, involving quantum mechanics, but their fundamental operation relies on understanding energy and matter interactions at a level consistent with Einstein's early work on photons and energy. Quanta, remember, Yves Sifo came from that same miracle year, 1905, along with his work on the photoelectric effect, which introduced light quanta.
It's all connected, yeah. The understanding of light and energy was crucial.
And then obviously, the most direct consequence of immense oxynuclear energy, harnessing the enormous power released when you convert just a little bit of mass directly into energy in a controlled way.
And beyond technology, general relativity became the essential toolkit, the mathematical language we needed to even start thinking about the most extreme things in the cosmos.
Like what?
Well, concepts like black holes, for instance. Regions where gravity, the curvature of space-time, becomes so intense, theoretically infinite at the center, that nothing, not even light, can escape. That idea comes directly out of the equations of general relativity.
Couldn't even conceive of a black hole with Newtonian physics?
Not really. Or the Big Bang Theory, the idea that the entire universe expanded from an incredibly hot, dense state billions of years ago. Understanding that expansion, the evolving geometry of space-time itself, relies entirely on general relativity.
It gave us the framework for modern cosmology.
It really did. And it lets us explore even more exotic theoretical ideas, like wormholes, hypothetical tunnels or shortcuts through space-time allowed by the theory's geometry, although we have no evidence they exist. But the point is, relativity provides the language to even ask these questions. Without it, our view of the universe's history, its structure, its most extreme objects, would be incredibly limited.
So it gave us the tools to understand the universe on the grandest scales and in its most intense conditions.
Exactly. But the source material also brings up something maybe deeper, a kind of philosophical takeaway, almost a life lesson embedded within the physics.
What's that?
It goes back to that core idea we started with, the train example. The fact that what you see, what you experience as reality, fundamentally depends on your frame of reference, where you are, how you're moving.
Right. The person on the train sees the ball go straight up and down. The person on the platform sees it arc forward. And both are right from their own perspective.
Precisely. And this fundamental scientific principle, that observation is relative, translates surprisingly well into a broader insight about, well, life, about how we interact with each other.
How so?
It suggests that reality can, and often does, look completely different to different people, based on their background, their experiences, their perspective, their frame of reference in life. And crucially, from their standpoint, their view might be entirely valid, entirely right, even if it seems contradictory or just plain wrong from your standpoint.
Huh. That's actually a really powerful connection, taking this complex physics and seeing it as a metaphor almost for understanding different human viewpoints.
It sort of encourages a bit of humility, doesn't it? An openness to the idea that your own perspective, while perfectly valid for you, isn't the only valid one out there. The universe, scientifically, is relative. And maybe human experience is too, in its own way. It suggests the importance of trying to understand another person's frame of reference.
So wrapping things up then, Einstein took these things we thought were simple time, space, gravity, motion, and showed us they have this incredible hidden complexity, this flexibility, this deep interconnection.
His theories didn't just adjust physics formulas. They fundamentally reshaped how we see the universe and our place in it, showing us a cosmos that's much more dynamic, surprising, and maybe still holds countless secrets.
A universe far stranger and more wonderful than we imagined before him.
And maybe the most profound thought, the final idea to leave you with from this deep dive, echoing the source's closing sentiment, is that this core concept, reality, isn't just for physicists thinking about stars and particles.
It applies to us directly.
It is the fabric of your own experience. Reality is relative to who you are, where you are, and how you are moving through the universe.
That's quite a thought to end on.
So maybe the next time you're moving on that train or flying high in a plane, just walking down the street, or even just standing still looking up at the stars.
Yeah.
Just take a moment. Remember, you're not just a passive observer watching a fixed reality show unfold.
I'm part of it.
You're an active participant within this dynamic, relativistic universe. A universe where time can literally stretch and slow down, where space itself can bend and warp, where even light follows the curves laid down by mass, and where your own perception of everything is intrinsically linked to your unique perspective, your unique journey through space-time.
It's not just abstract science out there. It's the reality we're living in right now.
It's the remarkable, surprising, relativistic reality you inhabit every single moment.